Usually when we think about manufacturing, it kind of brings up these images of um, brute force, you know?
Right, yeah, like blacksmithing or something.
Exactly.
Yeah,
Just
like,
hitting hot metal with a heavy hammer till it bends to your will. But step into the world of precision plastics manufacturing and, well, that blacksmith hammer is entirely useless.
oh, totally. It's a very delicate thermal tightrope. With steel, we know exactly how it behaves under a torch. It's aggressive, but predictable.
But plastics are a whole different beast. Welcome to today's deep dive, everyone. Our mission for you today is to unpack this highly specialized presentation deck we found on precision mechanical engineering vocabulary.
Yeah, we're going to be looking at 5 advanced manufacturing techniques for plastics used right on the R&D floor.
And we won't just be throwing vocabulary words at you, we're dissecting the actual physical impact on the materials. Because really, this whole list isn't even about cutting.
No, not at all. It's basically a battle against heat. Plastics are just incredibly sensitive to thermal changes when you machine them.
Right, like one wrong move, and instead of a precision part, you just have this melted mess on your hands.
Exactly. Which brings us to the first technique from the deck, CNC routing.
So the R&D application notes for this mention using a high-speed spindle with a single flute end mill, and that's to prevent friction-sensitive plastics like POM from melting.
Right, and that single flute part is crucial.
So I was trying to visualize this, and tell me if this makes sense. I pictured a crowded hallway. If your drill bit has multiple cutting edges or flutes, it's like trying to shove a massive crowd of people through a revolving door.
Oh, I like that.
The plastic shavings get trapped, they jam up, and it generates massive friction, like getting rope burn if you pull a rope too fast. Why does a single flute tool specifically solve that?
Well, continuing your analogy, a single flute is like throwing open a giant set of double doors.
Okay.
Yeah, the shaved material has plenty of empty room to just fly away instantly, and when it flies away, it carries the heat out with it. In engineering terms, we call that maximizing chip evacuation.
Chip evacuation. Okay, got it. But what if an engineer wants to eliminate heat entirely? The deck mentions a zero heat affected zone.
Ah, yeah. That leads us to abrasive water jet cutting. It's the ultimate cold cutting alternative.
Water jet. So they're just using water to cut plastic?
High pressure water, yeah, but mixed with abrasive particles. Since there's no mechanical friction from a metal blade scraping the surface, the material stays structurally perfect.
Wow. So no heat at all.
None. It's the go-to for cutting thick plates of temperature-resistant plastics, like PEEK. You avoid thermal deformation entirely.
Okay, so if water jets handle thick, heat-sensitive plates, how do engineers approach thin parts, like for rapid prototyping?
For thin parts, the vocabulary shifts to laser cutting, specifically using high-energy evaporation.
Wait, hold on. I'm going to push back here.
Oh, really?
Yeah, because you just said we absolutely must avoid heat to prevent deformation. But lasers are literally concentrated high-energy heat. Why doesn't the acrylic just warp into a puddle?
It's a fair question, but it really comes down to time and thermal concentration.
Okay, how so?
The laser is so intensely focused and it moves so fast that it literally vaporizes the plastic in its path before the surrounding material even has time to absorb the heat.
Oh, wow. So it evaporates the cut.
Exactly. And the tiny amount of heat that does bleed over, it actually perfectly micromelts the extreme edge. It acts like a built-in flame polish.
That's wild. They're basically weaponizing a micromelt to their advantage.
They really are. The application here is fabricating those thin acrylic covers that instantly get a polished edge finish right from the laser.
But what if an engineer needs a complex 3D prototype fast, and they just want to bypass the thermal stress of cutting altogether?
Then the terminology shifts to vacuum casting. Because if you start with a liquid, you bypass the friction problem entirely.
Right, because there's nothing to cut.
Exactly. It's the fastest route for low-volume production. You pour an ABS-like liquid resin into a silicone mold, but you do it inside a vacuum chamber.
So the vacuum pulls out all the air.
Violently pulls out every microscopic air bubble, yeah. It ensures a perfectly dense, flawless, solid housing.
Okay, but what happens when a plastic is just simply too soft to hold a tight tolerance? Like, regardless of whether you bypass cutting or use cold water.
Oh, that's where we get to the ultimate R&D term, cryogenic machining.
Cryogenic, like freezing it.
Yep. It's brilliant applied physics. Some materials, like PTFE, which you probably know as Teflon, they are naturally really soft and prone to shifting.
Right, Teflon is super slippery and kind of squishy.
Exactly. So cryogenic machining uses liquid nitrogen to temporarily freeze and harden those soft materials.
Wait, really? They freeze the plastic.
Yeah. Say you need to maintain incredibly tight dimensional tolerances on a PTFE seal ring. You freeze the plastic, you machine it while it behaves like a rigid metal, and then you just let it safely thaw back to its soft state.
That is just so cool. So to you listening, the next time you look at a perfectly fitted plastic component in your daily devices, just remember the intense thermal battle that took place to make it.
Truly, from vaporizing lasers to liquid nitrogen freezing, engineers are practically wrestling with thermodynamics to get that perfect shape. It's incredible. And it makes you wonder if engineers can temporarily freeze soft plastics to machine them like rigid steel today, what other fundamental material states might we alter to manufacture the impossible tomorrow?
It's a great question. We're literally reshaping reality by changing the very nature of the material itself.
Definitely something to think about. Catch you on the next deep dive.